in terms of collisions, there's just two cases that you got to be able to break down. One is called an elastic collision, and then one is called inelastic. What's the difference? Elastic is just a fancy word for bouncing. And in real life, it's actually hard to get a perfectly elastic collision. Most things will never be 100% elastic. When you have a 100% elastic collision, all of your kinetic energy is conserved. You don't lose any energy to, what would you mostly lose energy to in a collision? Theoretically, if I get this thing going, it should go forever and ever. But it actually doesn't. It actually stops pretty quickly. What does a Newton's cradle slow down over time? We're losing energy to friction. Good job. As the balls collide, thermal energy to heat. If we could actually measure the temperature of the balls, we would see they would increase slightly. Some to air resistance and to sound, obviously. But if these balls were perfectly elastic, they were like super ball material, this would go forever and ever. And all it is given any two objects, or three or four, we'll just start off with two, that has a certain mass, we'll call it m1, a certain velocity v1, a second object that has a certain mass and velocity m2, v2, then after the collision, we could measure its mass and velocity after. That's that. You guys ever do this prime notation in math? You do that little tick mark? I want to point out some of your textbooks, including ours and like a college textbook, they might call this m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. And some college books even use like the letter u for the initial velocity. It doesn't matter the symbol, it's the idea. So I just like the prime notation just because I think it's a little bit quicker. m1 v1 and just add a little tick afterwards. Now the second kind of collision you can have, oh, that's just wrong. Shouldn't look at man boobs early in the morning there. Eee! But in a sumo collision, or whatever, or most collisions are what's called an inelastic collision, where two things will crash together and they'll stick together. So if you look at this, we have two objects, m1 v1 plus m2 v2. When they stick together, you have to combine their masses, and then they have a final velocity, they move together. Big time inelastic collisions, you lose a ton of kinetic energy. And then the other thing you got to be careful of is momentum and velocity have directions. So you have to be careful of going to the right or left. So the best way to see this equation in action is a couple simple examples on our collision card here. So let me just show you a few here, and I'll just see if the webcam will capture it, no biggie. So I'm going to send this part this way, which is to your right. Okay? So let's say this is 1 unit of mass, obviously, right? And we'll send it with 1 unit of velocity. Okay? What's cool about these these cards, I kind of give away, they're like bumper cards. There's little magnets in there. There we go. And you can kind of visually see that before my collision, this is an elastic collision. If this card has 1 unit of mass, 1 unit of velocity, and this card is not moving, does it have momentum? Card number 2, or there is no momentum? Any momentum here in the second card? No. So the total momentum before my collision, if I look at m1 v1 plus m2 v2, would just be 1 unit of momentum overall. I mean, we could actually mass it in kilos, get the velocity, but conceptually it's just good to see. So in other words, if I have 1 unit of momentum before the collision, I must have 1 unit of momentum after the collision. Now the opposite of an elastic collision would be what? An inelastic collision, right? Where you actually stick. There we go. 1 unit of momentum hits a second cart and they stick together, right? Then the total system afterwards must still have what? 1 unit of momentum, right? But if I have twice the mass, bam, it's got to move at exactly what? Half the speed. And in real life, which kind of collision is more dangerous? Getting hit by a car, or say like by a huge bus or pickup truck? Yeah, exactly, right? So now if I double the mass, that's what I did, I added extra weight, I would have 2 units of momentum, right? So if I slam into the little car, bam, it's going to now move with 3 units of mass, right? At, let's see, if we have to get 2 units of 3 times 2/3 the initial velocity would give us 2 units of momentum overall. So in other words, conceptually, you kind of get this idea of momentum conservation. So in the end, by applying the big idea of momentum and conservation in terms of collisions, we can tie together all 3 of Newton's laws. Newton's first law is the basic definition of momentum. It's inertia in motion. P equals mv. Newton's second law, net force equals mass times acceleration. You can get the impulse equation, Ft equals m delta v. And then finally, Newton's third law, the law of action-reaction, we could come up with their conservation of momentum equation there. So the big idea is momentum ties in all 3 of Newton's laws, and conceptually, we apply this all the time in real life, whether it's in sporting events or looking at collisions and such there.